Okay, here we are at our final session. I'm going to be talking about the perfect reliability program plan. You ready? I always get asked this question. Can we make the perfect reliability program plan for our organization? And I always give the same answer. No, you can't. Nope. I will never even try to sell or condone such an idea because it is fundamentally flawed. Why is it fundamentally flawed? A plan is specific to a product and program. That's very important. There can't be a generic plan that is in your company that you just automatically pull out and use for every program. It'll be ineffective in every program. And I'm going to go through the reasons why it has to be specific to the program that's going to be it's going to be a part of. It actually won't even be the right program plan at the end of the program. As you're going through the program, the needs will change. The landscape you're standing on will change. The reliability program plan has to change. It has to always fit. If it doesn't fit with all the other parameters, it's not of value. We also then need to figure out how do we change the reliability program plan? Do we have tools or do we just do it ambiguously? I mean, we're in the middle of the fight. We're frantically trying to execute our duties during the program. How do we stop and reevaluate it and decide to make changes? It's very difficult to do. So we need some actual mechanisms that will help us have the reliability program plan evolve as we're going through the product development. So let's discuss the components of a plan. You have schedule, budget, and product goals as three main reasons why you need a plan. This is not just a reliability program plan, this is obviously the entire program plan. These factors even go into why you're even doing the program, right? What's the point of having a reliability program plan that doesn't consider schedule? You just put everything you possibly want to do in there. That's not helpful because then it has to be audited and edited as you go through, and who knows what's going to get cut out. Not to mention the credibility of these requests falls away greatly if you haven't even put in things that can be executed in the time frame. The second is the budget. Why would you put in activities that can't be funded? This doesn't make sense. This is just a silly wish list that I see quite often. People make these plans that cover everything. And everybody knows, even the person creating it, that there's no way to execute it all. It's not going to be funded. So again, the credibility is lost with these reliability program plans, and they get dismissed entirely. And then the goals for the product. This is critical. If the product is going to have, has the legacy products, but it's going to have some really amazing new technologies developed and incorporated, that has to be considered. That's a very important goal. We can't just be advancing reliability or using reliability for certain parts of the product. These new parts that are being developed, they have to be incorporated and have the right tools addressed to it. So these are three very important factors that are included. So this is what's going to help us select the reliability tools. We need to be expert in the tools, not because we want to throw them all in. We need to be expert in the reliability tools so we know which ones to pick at the right time. Wouldn't it be ridiculous to write a plan for a mechanic fixing a car that said you have to pick up the 12-millimeter wrench at 2 o'clock on Thursday? That doesn't make any sense. What occurs is, the way the plan's written is, there's an activity that has to be done, removing something to try to diagnose it, and he has the knowledge of the tools to know what tool to grab to do it. That's where that becomes incorporated, when the expert who knows the tools selects the specific tools and doesn't throw the whole toolbox at it. What we end up with, hopefully, is our product that satisfies the schedule, the budget, and the product goals. And that's what the plan should do for us, is we create a reliable product in conjunction with the higher level program goals. So let's take a look at one tool, design failure modes effects analysis. I spoke about this in an earlier session. The idea is to identify risk and prioritize the actions because we have limited resource. So we have our key factors, which is severity, occurrence, detectability, and the risk priority number. I talked about how those are the quantifiable measurement factors. And why am I talking about DFMEA? Because DFMEA creates an output that helps us select the right tools, right? Remember I talked about 3 of those items there for our inputs were the schedule, the budget, and the product goals? Well, schedule and budget, those are limited resources. The point of a DFMEA is to help you allocate resource to the areas that are of greatest risk. I don't think people realize, but a design failure mode defects analysis, it's really a project management tool more than a technical tool. Stop and think about that for a moment. That's really the need that should drive it. So that's how we're going to have help selecting the right tools, which I showed as being a needed input on the other side to get that product that we want. So with the scale and acknowledging that tools tend to fall on a linear scale between measure and improve and some balance of it, and then also taking that in consideration, the bathtub curve, we'll find some of these tools, such as HALT testing, which we've discussed in an earlier session, and how it applies to providing very valuable input to improve. Stress margin testing, which helps us understand the relationship between the failure modes and the stresses that occur. We have reliability growth testing. And reliability growth testing is one of the ones that provides a very valuable measure. So when we're talking about the reliability program plan, the measure part is a big deal because that's part of what helps us decide how to respond and change what we're doing. Reliability growth offers a constant feedback of confidence growth for the program. Now there's something very interesting about reliability statistical confidence that's different than the other metrics that we commonly use. What's different is that it's measuring us. It's not measuring the product. Reliability is the product's performance. Getting confidence in our reliability is measuring how well we believe we understand how that product's going to perform in the field. So you're going to make a statement when you release the product of we're 80% statistically confident in our 99.99% reliability. So why is this important with regard to if you know your reliability program plan or program is going to change? Because you're going to set milestones at your different phase gates, as Tim was talking about phase gates and product development. You can set a confidence that you want to have at each phase gate. You can say at release, we want to be 80% confident. We've done testing programs that we are 80% confident. That means that at phase gate number 2, we should be 20% confident. Phase gate number 4, we should be 60% confident. And that's going to be the trajectory that gets us there. Why do you set those interim goals? Because if you get to the second phase gate and you're not at 20% confidence, you need to have a discussion. What's going on? Why aren't we? What do we need to do different? And if you sincerely have that discussion, obviously the value of that is you change what you're doing. That means your plan's going to change. That means you have to have acknowledged in advance that there's metrics throughout the program that may change your plan. So what kind of things might you find if you find out that you haven't hit that percentage confidence you want to be at? Well, the conversation always goes one of two directions. It either goes to the product's not performing, we're finding a lot of failures we can't root cause or identify yet, or the product's performing fine, we just don't seem to have enough test time to generate the confidence. Remember, we're measuring ourselves, right? How well we understand the product. And if we're not getting enough test time, we obviously don't understand it very well. Well, those two are very important to decide which one is causing the deficiency. If it's a product, you better start throwing a lot of money into the engineers doing more R&D in design and improving the design. This could be very lengthy. You're at high risk. If it's that you don't have enough testing going on, you need to ramp up your testing, but there's probably a good chance that if you increase the testing, increase the amount of measurement you're doing, as far as you know, your product's still fine. But both of those are big changes to resource and what you're doing in the project. So your reliability program plan has metrics and measuring systems built in that actually direct the changes to itself. It's self-monitoring and adjusting. It's a closed loop. So accelerated life testing, let's talk about this tool a little bit and how this works in the plan. So With accelerated life testing, it's very much a measure type of tool, as I pointed out on that gradient I had earlier. So with accelerated life testing, we're looking to characterize a specific wear-out failure mode, our dominant wear-out failure mode. And we've isolated the stress that drives it, and we've created a test. And we've compressed the time it takes to wear out by figuring out an acceleration model. And the information we hope to get some kind of a bell curve for that failure mode, right? There's going to be, if you take a large population, there's going to be an average for when they fail for that specific failure mode and some distribution around it. Now, what are we looking for? We're not looking for the average product to fail when it wears out. That means 50% would fail too early, right? We want that distribution to be farther out from the characteristic part of the bathtub curve that we have for our actual goal profile. Because if you recall, this is when we want the customer to discard it because the failure rate's going to increase. So we need a small part of this tail to come into there to be satisfactory. Okay, so that's what we're going after. We want to make sure it doesn't happen. So what happens if accelerated life testing starts too late? What if our plan set at beta we're going to start the accelerated life test, which is what we did last time and it worked out fine. But it turns out with this design, we weren't able to get as good of an acceleration model, which means we couldn't compress the test as much, which means we're going to find out about this distribution about 6 months after release. Where's the value? It's pretty minimal. You're just barely ahead of the customer, right, at that point. What are you going to do when you find out that you've way too many failures earlier in life? You have a total recall and redesign. It's frantic. And that's because you took your generic reliability program plan and just applied it to the new product without considering the specific details for this design and this program with its resources, needs, and new technology. So, yes?
Back to the ALT for just 1 second.
Yep.
The understanding that you get from HALT on the actual limits of the product will allow you to accelerate your ALT test because you'll know exactly what limits you can go to and try and speed up the process. Mm-hmm. So just one comment.
Yep, true. So reliability growth. So reliability growth can look like this, where you have your MTBF or percentage confidence that you want to demonstrate. And these are your hours you have available runtime. And you're going to be growing your confidence in your MTBF as you progress along. And then you're going to come to a point of where you've improved the product through the feedback and you need to validate it. Does validation happen? Or did we design a reliability growth program that only allowed for the initial demonstration? Remember I was talking about the phase gates and you want to demonstrate percentage confidences that line up with it? Well, that's fine, good and fine and all, but in reliability growth, you've closed out issues based on retesting of smaller subassemblies, not the entire system. You haven't validated the entire system can truly perform that way. And that often gets omitted. So this very critical validation phase will fall off the end of the program and be done after. You're effectively racing your customers to do it, or for all practical purposes, they end up doing your validation. And this is because you didn't line up the reliability growth program in all of its phases with the real program. So you should have made a decision that, hey, if this is what we project out for a number of hours it's going to take to demonstrate this confidence and we know from historically what kind of failures are going to occur, where does our validation end up? Do we need to put more resource to this? Because you can pull this in with a lot of reliability growth programs by simply having more samples and creating more runtime. So without having stopped and acknowledged that in advance, or at least considering what the budget and what it's going to limit, you again have greatly reduced the value. And there's really nothing worse than investing in a test and getting very reduced value from it, right? Because it's one thing to not invest in a test. It's another thing to invest in a test and get a lot of value out of it. But if you make people invest in a test and then you can't show much value, not only was that a waste, you've totally destroyed credibility going forward for next time you ask for it, because they're going to say, what did we get from you last time? You told us after we released about we were going to have an issue, and the customer was already saying that. So be very careful, because that can actually be worse than having never gotten funded in the first place. Because at least when you don't get funded and you have issues, that's actually an argument for next time, like, hey, can you please support these tools that could help? But when they can say, yeah, we did last time, but it didn't do anything, now you're in trouble. That's hard to recover from. So that's why the reliability program plan and having it be dynamic and include those inputs, like I said, the schedule, the budgeting, and the design goals is really critical. But again, I'm going to reemphasize the closed loop part of it. It's constantly monitoring and adjusting itself. So with HALT testing, as I described before in this example, you can see how by having HALT testing, they did a DFMEA early, very early, and identified a way to do a very simple test early with a subassembly. They didn't have to wait till the whole thing was made with a subassembly, and it yielded not just information about what was of interest to them, but if you recall, it yielded information about something that they hadn't even considered to be a high issue when they originally evaluated. It was a lower item that rose higher once the HALT test identified a very high likelihood of that connector coming undone. So here is a point of where, remember with the HALT testing, I was talking about including it in different parts of the program, and I say always do it as early as possible because of the rule of 10. Well, here's a time where if using that rule of 10, we're able to make the argument that this limited resource we have, we should put it here because there's a lot of, let's say, new technologies or features we're not familiar with. And the reliability program plan is where that conversation happened as you were creating it. So now, regarding that closed loop part and being able to do a much more quantitative job in creating the points for discussion, throughout years of struggling with this, I've come up with another tool. And it's the program risk effects analysis, and it's effectively the sibling, and I based it on a failure mode effects analysis. Now here's the difference. Failure mode effect analysis is looking to address risk to the product. The PRIA is looking to address risk to the program. So let's talk about what that is and how it works. And I wanted to bring something quantitative to it. And the PRIA has two factors that are considered: the impact to the program goals and the impact to the reliability goals. Because you're going to find with most of the points where we're trying to make decisions about resource in a program, those are the two sides that we're weighing when we're trying to figure out what to do. So impact to reliability and impact to program goals. So the reliability is warranty and sales. When you really think of it, that's the two fundamental arguments for why you want to improve reliability in a product. We're worried about warranty and we're worried about sales, customer perception. And the program, generally what we're worried about is time to market, and we're worried about features, because with the program, those are the two things that generally drive it hardest, is developing new features, and if those features have reliability issues, you have to make a choice. Do we not include the feature, or do we continue to develop it? And that affects time to market. So any reliability issue you find, that's usually where you end up stuck. And you have the project managers on one side, and you have the people concerned about the reliability on the other side, and you're debating the value of changing time to market to solve a reliability issue. Okay, well, debates will go on forever and just end with whoever has the most credibility, unless you have a quantitative way to address it, and that's what PRIA is about. So here's a set of scoring tables for those two sides, so we can actually make it quantitative. And you can see here why I say it's directly related to the principles in the failure mode effect analysis, is we create the tables the same way you would create them for severity, occurrence, detectability, so you can calculate an RPN number. Well, here I took those four factors that are typically the foundation for the argument: warranty, sales, features, and time to market. And in advance of the program, we create a scale. 3 factors is enough for a lot of them. But for warranty, 1 could be low warranty cost, 3 is low sales due to warranty and some from poor reliability, and then 5 is loss of future sales and high dollar warranty costs. Those are scores 1, 3, and 5. For sales, it could be 1 is we hit our target market share, 2 is we're 30% below our target, and the top one is 50% below. Then for impact to the program, what do impact to the program look like? Well, for features, it could be we included all our planned features. We were able to include them and they were all reliable. 3 is we had to reduce some functionality, and 5 is we had to eliminate some key features. At the last moment, we realized in the program we can't include this if the product's still going to be reliable. And then time to market. Obviously, on time is best, and you can pick 2 time periods that are appropriate delays based on what you've experienced in the past. So what do we do with these scales now that we have them and we're in the discussion? We create a factor like the risk priority number in DFMEAs. I call it the balance factor. And simply, the balance factor equals the impact to reliability product of its 2 variables, warranty and sales, minus the impact to the program goals, which is time to market and features. And we simply subtract them. So what do we do with that information? Because now the balance factor has a number. Well, if it ends up being that it's negative, then we should stay with the freeze. It should be held. The freeze being the point in the program where we realize we need to stop and address what is going on. If it turns out to be that the product impact's greater than the program impact, which would make B positive, then we should be flexible with it. So you can see how it's very simple. There's nothing amazing or brilliant in there, but it's simply taking that argument that we have in kind of abstract terms and putting quantitative values on it, and the argument is based on tables that we all agreed upon in advance of the program. So you end up, if you disagree with how this resulted, you end up arguing with yourself, an earlier version of yourself that did agree to the tables. So this is another way to create that closed loop, the closed loop characteristics you can have for a reliability program plan, where it is monitoring itself and able to change and evolve as the conditions around it change. So it needs to be dynamic, a good reliability program plan. It has the right tools. We've taken time to pick the right tools and put them in the right place at the right time. We're not just following a process of, hey, we always do HALT first, we always do reliability growth second, we always do accelerated life testing third, because that's what we did last time and that's what we always do. They're in response to having identified the needs accurately. And it's supported. We've created support. You have team input and buy-in because you've asked for the input in advance. You've asked for the sales, the marketing, the project managers, quality, manufacturing, and they provided that input, and that's part of what helped you select the tools to adapt and connect to what is important to them and they're trying to deliver. Now everybody's a part of that reliability program plan, and the fact that they were part of it in the beginning also means they'll be a part of it as it transitions to adapt to the program. And that's how to make the non-perfect reliability program plan that can never exist as a generic plan for your company. It needs to be specific to your product and program. Other questions? Another perfect presentation? No questions? Fantastic. Good. Okay. All right. Well, thank you, everybody.